Okay, so this disk method is pretty interesting. What we're going to do is attempt to find the volume, which is 3 dimensions, of some kind of figure we're going to create by revolving around an axis of revolution using kind of like 2-dimensional functions. Okay, so here's the idea with the disk method. So let's start with this example. Suppose we're asked to find the volume of a solid generated by revolving the region bounded by the graphs of the equation about the x-axis. Okay, so this is a real common way that you'll be asked this question. So you'll kind of give boundaries of an area, right? 2 dimensions. And if I graph that, this is just the line y equals x. That's the function. And then these are just kind of bounds, all right? So you just did area with the curve. So that's really helpful for this because we got to kind of start with the area, all right? And then what we're going to do, so we revolve it around the x-axis. So what happens there? If I just take one slice of this guy, like imagine right now it has no width, and we revolve it around, you're going to get a disk, right? If you can picture it, you just revolve it around and you get this like this is kind of a side angle, a little bit of it. You would get a disk, right? Because it wouldn't be rectangular because when you revolve, you're making a circle, right? So you get this like what we'll call a disk right now. It looks something like that. And then if you did it for all values over the interval, you get a bunch of disks, right? And then this would kind of look like that. And then you get this 3-dimensional cone, what really is a cone. All right, so if I just take a look at one of these guys, what I start with is, well, a rectangle. We're going to get to that 3rd dimension here in a second, but imagine this has no width and you revolve it around. What's the area of one of these disks? The area would be the area of a circle, right? As you rotate it around, that's going to be a circle. So you get pi r squared. That's just the area of like one of these guys, okay? And now if I want to add this width to it, right, what's this distance here? It'd be delta x. That guy looked familiar. Remember that from Calc 1? Delta x. So if I have a disk that now has some width to it, I now have 3 dimensions, right? And the area of the disk would be the volume of this disk when we rotate it around now has a 3rd dimension of width. You would just multiply the area by that width, and then you get the volume of just one disk, okay? Now what we want is the volume of this entire thing. Okay, so this whole thing looks, right, it's just this big cone. And I can do that using calculus. Okay, so first of all, what's the radius? The radius is the distance, let's switch colors. The distance for any one of these guys from here to here. So let's just focus on this one, this disk right here. And the radius is given by the function, right? Sound familiar? That's what we did with the area under the curve, right? It's just the distance from here to here, which is given by the function. So that's f of x squared. And then the delta x is just the width of one of these rectangles that we're rotating around. So in this case, so now this is volume of one disk is pi, and in this basic case, f of x is just x. Okay, and now if I want to add these all up, like all of these disks that have a little bit of width to them, we can do that. What do we do when we add up a bunch of areas? Well, we integrate, and I go pi times the function squared, and then this delta x over integration when we add everything up. Remember when we went to like the long way would be to add all these guys up, and then we transitioned using the fundamental theorem from adding up a bunch of things. We realized that was integration, and then this delta x becomes dx, and that gives me the sum of all of those disks, and I'm integrating from 0 to 4. Okay, And that's it. That's the disk method. Whatever I get for that will give me the volume of that cone, which is pretty cool using calculus, really calculus stuff we learned from Calc 1, single variable calculus, I should say, even though we end up with a three-dimensional volume. So let's finish it off. Now it's easy. Like the hard part is setting it up, right? I'll never really give you like a really complicated integral to do. We'll do that later. That comes in chapter 8 when we do like complex integrals. But right now, I think the main part's going to be figuring out what the setup is. All right, so once we get that, hopefully the integral won't be that bad. So let's integrate x cubed over 3. The constant comes along for the ride. And we go from 0 to 4. And we're done. That's 4 times 4 times 4 is 64 over 3. All right, that's pretty cool. Let's check our work. We could have done this the easy way because this is a right circular cone. So you can look up like the volume of a cone formula, and it goes like this. It's pi r squared times h over 3. All right, that's a geometric formula, and the height would be the distance from here to here. That is from here to here, which is 4. That's along the x-axis. So pi times 4. And then the radius is the y value. And they're the same in this case because it's the line y equals x. So the radius is the distance from here to here, which is also 4. And we can see this way is a lot quicker, but you're not always going to have a geometric figure that you realize. We'll do some more complicated examples. If the curve's like y equals x squared, there is no figure that represents that. So that gives me 4 cubed, which is 64 pi over 3. So we know we're right. But this way is a lot more interesting, right? We're integrating, we're using the function, we're using the concept that we're adding up a bunch of little rectangles as over really small changes in x. Okay? That's the disk method. Now, let's talk about the washer method, because it's really the same thing. When you hear disk, think washer. Washer, disk, same thing. The washer method is just 2 disk methods. For example, if I rotate this guy, if I want to rotate this region, bounded by x squared and root x, I would do kind of the same approach. I draw a little rectangle, right? And then I rotate it around the x-axis. So you have this gap. All right, and this is why it's called the washer method, because if I rotate this around, right, this would be down here, and you would have this like, you'd have the disk, but there's going to be this hole in it, right? So you get what we call a washer as you rotate around. I'm not the best at drawing these, but I have, this is what it looks like. One of those would be, if you look at this like from the inside, then you have this washer. Right, that would be this guy rotated around. So what do you think? You might be able to come up with the formula for this. Maybe take a pause. It's just an adjustment of the disk method where you have to subtract one disk from the other, right? Take this big disk and subtract the little disk. It's 2 disk methods. Why don't you pause, see if you can work out the formula. All right, so for the washer, the area of one of these without the little thickness would be the big radius squared. So it's still pi r squared, right? Pi r squared for each of them. So for this larger radius, this guy right here, I'll use capital R. And then what would you do? You would just subtract this smaller radius, right? And that would be small r. And then if we add a little bit of width to this guy, then we need a delta x. And now we have 3 little, barely 3-dimensional disks, right, with a little bit of width. And then if I want to do this for every guy, so if we rotate it around, we're going to get this thing, and then it look like that, and something like that, right? And you'd have this shape, but there'd be, if you look at it from the middle, there'd be a big hole in it, right? Here's a better picture of that. My picture is not bad. All right, so it's just two disks, right? You're just subtracting one big disk from that, a smaller disk. And if we want to add them all up, then we're integrating. And in this case, we realize they intersect at x equals 1. So we go from 0 to 1. I can factor out the pi. And then I'm going r, and r is a function of x, and that'll be important later, minus little r of x. And we're squaring that from the formula for area of a circle. And then over integration, delta x is dx. And that's it. That's my formula. And then what are your rx's? Let's finish this problem. So the big radius is the root function, right? Let me make sure I check. Nope. Yeah, the root function's on top, just like area of a curve. So I go root x squared minus x squared squared. And I have my multiple of pi. And then I integrate. So remember, root x squared is just x. And of course, x squared squared is x to the fourth. So this would be x squared over 2. And this would be x to the fifth over 5. And then I'm integrating from 0 to 1, which is pretty easy. I just plug in 1. So I'm starting with some easy examples. So I plug in 1. I get 1/2 minus a fifth. So that's 5/10 minus 2/10. That's 3/10. So that's 3 pi over 10. Pretty cool, huh? That's the volume, right, of this crazy looking figure, and we can do it pretty easily. We know the exact volume is 3 pi over 10. Let's see. Let's do one more. Okay, so I want to rotate around. I got to tell you what axis to rotate around. So x-axis, because eventually we're going to be able to rotate around using the same concept. I can rotate around like this line. Or I can rotate around the y-axis. Or I can rotate around the line right here. All right, we're going to be able to do all of that here in a little bit. But first, let's keep it with the basics so we can learn the process and just do the x-axis. And we're going to do the disk. I kind of think of them as the same, disk / washer. Right? Washer is just two disks. All right, you're subtracting that empty disk. So I might want to graph this negative x squared plus 4. I know what that looks like. It's a parabola that goes down. I think my x-intercept should be at 2. I know what this line looks like. Y plus 2. X plus 2. That's here and has a slope of 1. So it goes like this. So this is my region. Okay. So if I want to find out where they intersect, I'm going to have to, let's see. I think let's blow this area up a little bit so I can draw my little rectangles that I'm going to rotate. Okay, so this point, what point would that be? It looks like it's x equals 1, but I want to be sure about that, so I can set these equal to one another. Negative x squared plus 4 equals x plus 2. So I'll move everything to the right, so that's 0 equals x squared plus x minus 2. And then I factor, and I get x minus 1, x plus 2. So my intersection points are x equals 1 and x equals negative 2. I'm not worried about negative 2 because I'm asked to rotate around the line x equals 0. Oh, x equals 1. They're telling us that. So we didn't even have to, but we can figure out where the region is bounded. And then it's not really bounded back here, but they're telling us to go from 0 to 1. Okay? So I go from 0 to 1. I got pi. And I got big R squared minus little r squared. There's your formula. All right, and then I just have to figure out which is which. All right, the concept, the idea, but it always helps. You could just work the formula, but it always helps to kind of like draw your little rectangle here, because you know it's big R is the distance from here to here. And then little r, of course, is the same idea. It's the distance from your other function down to the x-axis. And then you rotate it around. All right? So that might help. Or you realize, I mean, these are going to get more complicated as we go. So big R then would be negative x squared plus 4 squared. That's my quadratic. And little r is my line, which is x plus 2 squared. And then this is why sometimes I'll just ask you to set these up, because like on a test, for example, I might just say, set up the integral that represents the volume of a region that you would get the volume of a three-dimensional figure that you get by rotating the region bounded by all that stuff around the x-axis? And the answer would be this.